Okay, that's Spherical Coordinates, Lecture 4. Remarks about spherical coordinates in R3. You see? Classical mechanics. Electromagnetism also. You see? Now, the item I is notation. You see, you find in the literature, instead, if you use r, theta, and phi, you see a swap in theta and phi, okay? And this here, we can find in publications, some publications, and also in the relativity theory. The relativity theory, you just use this notation here, okay? I would prefer this one here. Why? You see, although this notation is used in the theory of relativity and in other publications, I do prefer to use r, theta, and phi, since it aligns to the cylindrical coordinates. You see, if I use here theta and phi, this theta aligns what you did on lecture 2 for cylindrical coordinates. In cylindrical coordinates, you use rho, theta, and z. Theta is the same in cylindrical coordinates and spherical coordinates. Z is the same in cylindrical coordinates and Cartesian coordinates. You see, that's I derived, you see, using this notation over here, okay? But if you study in some publication and you see this notation, you just swap, okay? All the derivation you did, you swap theta and phi. See there, you have the expression. Now, the second one, you see, is a basis vector. You see, there's a drawing about the basis vector. You see, phi is not latitude. Phi is, in this case, is co-latitude. You see, because latitude, with the Earth analogy, it starts from the equator, okay? And this is from the North Pole, okay? And phi, you see, is in the range between pi and 0. You see, the pi and 0. On the other hand, the azimuthal longitude, you see, the range is between 2 pi and 0. So it's rotate. Attention now. It's rotation here, the direction, the positive direction, is, let's say, in the counterclockwise, okay? So, and then it's important here, you see the direction, because this will be influenced on this direction of this basis vector. You see, because phi increases from the North Pole, this vector here points in this direction. Likewise, theta that rotates, a theta points that way. And AR, okay? This is point radially, okay? That's radius A. That's it. That's for you to see clearly this basis vector. Also, you could substitute, okay, the blue, red, and green one by its respectively unit vector, okay? So, attention now, just to call attention here. Look, ER, E theta, E phi. This is ortho normal basis. See this one. But AR, A theta, A phi, they are orthogonal, but they are not orthogonal. So I'll emphasize here. Let's put an arrow here. ER, E theta, E phi are orthogonal basis. When I normalize, then I'll get orthonormal basis. Okay? That's very important, because here's the dot product. Or is 0 or is 1. Exactly like in the Cartesian coordinates. And the third remark, this I would like you to develop. Okay? This is you use the cross product just deriving, okay, calculate these determinants. When A1, A2, A3, B1, B2, B3, they are the components, okay? Those are Cartesian, attention now, those are Cartesian components, okay? Because we expressed AR, A theta, A phi in terms of E1, E2, and E3. So this you can apply this, okay, just to check AR, A phi cross A theta. You see here, look, AR, okay, this A sub phi, look, if you rotate, okay, you reach A theta. So there's a point of the R position. Likewise, E sub theta here, you see, this is obtained by ER. A trick for you. Say, look, I can write this one, that's a trick. R, let's put theta and phi. You see, this is a permutation. You see, after R comes theta. After theta comes phi. So you look at here and you write, that's from here, you see, after R is theta. After phi is R. You see, after phi is R. And after theta is phi. Just look at here. After theta is phi. After R is theta. And after phi is R. You can write, okay, from here, just looking on this permutation. Okay, so that's it. Don't forget to check this, a good exercise.